So in this video, we're going to talk about sort of an introduction to computers, so how computers actually run code, how computers take code and turn it into a program, that kind of thing. And I'm also going to introduce just some fundamental parts of Java, which we'll get into in the next videos. So some things we'll cover in this video. We'll talk about an introduction to what computer science actually is. We'll talk about hardware, software, and programming language fundamentals, some different elements of a program, an overview on what source code is, an overview on what compiling is, and a very brief history of Java itself. So this course, CSCI 1250, is designed to teach you programming fundamentals. So let's just kind of define what programming in general is. So we know from our discussion a couple weeks ago that a computer is inherently kind of dumb. It can't make assumptions. It can't know what you're thinking. We actually have to tell the computer what to do. So we use the computer as a tool, right? Like this first point here says, a computer is used as a tool to perform some kind of task. And the computer has been programmed by someone to do so. We've discussed before that computers are just machines that follow instructions. And our instructions that we give the computer is what our source code is. So we're telling the computer to do a set of things. It will see those things and it will do them. Computer programming is both an art and a science. A lot of people think that it's just science, but there is a sort of art to it as well. And we'll discuss what that is. So how is programming like an art? Well, we've discussed algorithms, we've discussed flowcharts, logic, all that stuff. There's a lot of design that goes into programming, and all of that design kind of makes programming a sort of art. Every aspect of your program, like it says here, should be carefully designed. And there are things that must be designed for any real-world computer application that you end up writing. Before you even write the code, right, there are things that you should always include in your design of your program. Something like a logical instruction flow, which we've discussed algorithms before, which is just a sequential set of instructions. You can take an algorithm, right, because you have logical instruction flow, and you can turn that algorithm into a functional program. Any mathematical procedures that your program will use, how you want your programming statements laid out in the source code itself, the visual appearance of any screens that's in your program, how you relay information to your users, and then any kind of user manual, documentation, a how to use guide, a setup guide, anything like that. All of that needs to be designed in like a real life computer application. So there's some art there, right? There is a lot of science to programming, of course. We have a lot of writing, analyzing, experimenting, testing, redesigning, so on and so forth that we do with every program that we write. And all of these things are very scientific, right? We're writing our code, we're analyzing what works, what doesn't work, we're experimenting, we're testing, does this input result in an error? Or does it not result in an error, right? All of that stuff is very scientific. So we use a programming language. In this class, we're going to use Java because a computer does not inherently understand English or human language, right? I couldn't just sit down and write a text file that says, computer, add 2 and 2 together. That phrase in English, the computer would not know how to do that, right? So we would need to use some kind of programming language that would turn our English, or whatever language we speak, into a language the computer can understand. And we'll talk a little bit about that here in a few minutes. But there are strict rules to programming languages that must be carefully followed. Java has its own set of rules. C++ has its own set of rules. Every programming language has rules that you need to know in order to have your programs function properly. And that's also very scientific. So you need to know these rules that the programming languages have, and you need to follow them. Moving on just a little bit into some different parts of a computer. So we're going to talk about hardware, software, that kind of thing. Hardware, if you don't know, is just a physical component that a computer is made of. And when I say the word computer, it's not really an individual thing. It's a system of devices. So they all kind of work together, like it says here. If you want to think about an orchestra is made up of several instruments, right? Just like an orchestra, a computer is made up of several devices. Every one of those devices plays its own part. Your typical computer system will contain the following major components. So we have the central processing unit, we have our memory, we have storage devices, and we have our input and output devices. So we'll talk a little bit more about those. The central processing unit, or the CPU of our computer, the main functionality of the CPU is to fetch instructions, follow the instructions that it fetches, and produce some resulting data based on those instructions. So what are those instructions? Well, we call those instructions a program, right? So a program is just a sequence of instructions that is stored somewhere in our computer's memory. When the computer runs the program, the CPU will engage in this cycle here. So it's called the fetch, decode, execute cycle. And what that cycle looks like is the fetch step refers to when the CPU will fetch the next instruction from memory. So if you want to think about our instructions as just kind of waiting in line, the CPU is going to fetch the next instruction. Decode is the next step. Our instructions are encoded in the form of a number. The CPU needs to decode that number and generate a literal electronic signal, right? It's going to do something with electricity here. And then the execute step, that electronic signal is going to be routed to some component of the computer. So if we want to think about our instruction is maybe I want to open up a file, right? I want to open this picture. So decode, maybe the CPU will do fetch first. Fetch, the CPU would fetch that instruction. So I want to open up this picture. Decode, it will decode that number. It will send an electronic signal to probably our hard drive or wherever that picture is stored. And that electronic signal that's sent will cause that component to do some kind of action. So it's going to send it to the hard drive. The hard drive will probably return the location of the picture, and Windows or Mac or whatever you have will, open the picture up. Right? So there's a little sequence here. So moving on from the CPU, we'll talk about our memory, or our RAM. So memory and RAM is kind of the same thing. A lot of people confuse memory with storage. So storage refers to, how many things you can save onto your machine, how many files you can have, how many games you can have. That's storage. Memory is different. And we'll talk about what memory does here. So main memory, we commonly call this RAM, which stands for random access memory. And what RAM does is it holds these sequences of instructions in programs that are running and the data that those programs are using. So if we go back to our CPU, we see that the CPU cycle, the first step is the CPU is going to fetch the next instruction from memory. Right? So what is memory? That is our RAM, right? And it's just going to hold a sequence of instructions based on whatever program you have running at the time. So PowerPoint would have its own sequence of instructions in RAM. If you play games, they would have their own sequence of instructions, so on and so forth. So RAM doesn't store files or anything like that. It just holds instructions in programs and any data that the program would be using. Now, RAM is a type of memory that we call volatile, which means that it's only used for temporary storage. So volatile memory, if I were to turn my computer off, all of my volatile memory would be erased. All right, so if you had 10 games running on your computer, and you pulled the plug on your computer, right? All of the instructions and data from those games that were stored in RAM would be erased because it's volatile. You can't get those back. This is different than storage, right? If you were playing a game and you saved your game, your save file would probably be stored somewhere on a storage device, and you could, boot your computer back up, reload that saved file, and you would be good to go. Moving on from RAM to input and output device. Input devices are simply any device that collects some form of data and sends it to the computer. So think things like your mouse, right? Your mouse takes in your clicks. That's some kind of input that you're giving the computer. The keyboard takes keystrokes. Your flash drive would take in whatever files are on it. If you want to think about like a webcam as an input device, a microphone, anything you're giving something to the computer with is an input device. An output device is anything that returns data from the computer to us, the user. So our monitors or a speaker. I have a flash drive here on input and output, right? Because you could give the computer a file from a flash drive, and the computer could also save something onto the flash drive. So flash drive is an example of input and output devices. Another example of something that's both input and output is like a phone screen. If you have a smartphone, you tap the smartphone screen, and that's how it gets your input. But the smartphone screen also is giving you information as an output device, right? So let's talk about software. So we just talked about hardware. We discussed, the different components of hardware. Let's see, where was it? The CPU, the RAM, secondary storage devices. So things like hard disks and solid state drives, flash drives, stuff like that. And we talked about input and output. So now let's move on to software. So as opposed to like the physical components of a computer, software refers to the programs that actually run on your computer. So there's kind of two categories of software that we talk about: OS, or operating systems, and applications. So think about things like Windows, Mac OS, Linux, all of your operating systems, Chrome OS. Those are all operating systems. And an operating system, like it says here, is basically just programs that manage your computer's hardware and controls your computer hardware processes. Right? So your OS kind of handles that fetch decode cycle that the CPU does. The OS kind of handles all of that. Applications, on the other hand, are programs that solve specific problems or perform general operations that satisfy the needs of the user. Right, so think about Microsoft Word. Right, Microsoft Word is not controlling your CPU's fetch cycles. It's just letting you type stuff in and format it, right? That's an example of application software. A computer game, I have League here as an example. League is not controlling your random access memory's processes, right? The operating system is doing that. League is just a game that you play. So those are our two main kinds of software. We have operating systems and application software. So moving on from the parts of a computer, we're going to talk a little bit about programming languages. We've already said that a program is just a set of instructions that a computer will follow in order to perform some kind of task. Right? Very similarly to an algorithm. If you want to think about a program as a lot like an algorithm, where we said an algorithm is just a sequence of instructions that need to be ordered, right? So a program is pretty similar to that. It's a set of instructions that the computer is going to follow to perform a task. And we write programs using a programming language. All right, so before, we were writing our algorithm in English. So think about that palindrome lab we did. Maybe your first step was to, type out the word. Maybe your next step is to reverse the word, right? All of that's in English. If we wanted to actually write that as a computer program, we would need to use a programming language. So here's an example of a program. This is just a list of instructions. So this would be like our algorithm here. It's an ordered set of instructions. So let's just say we want to write a little program that takes the user's first name, converts it to all uppercase letters, and displays it to the screen, right? So our set of instructions might have, the first step saying, display a message to the user, what is your first name? Our second step would allow the user to type their name in. Our third step, once the user enters their name, we need to store that in memory, right? And let's think about RAM again for a second. We said RAM stores the instructions for our programs. RAM will also store any data that our programs use, right? So if we write a computer program where users are typing in their names, when the user types in their name and hits enter, that's going into our RAM, right? If we turned our computer off, that would be lost forever because it's volatile. So we store their name. Our next step, maybe we convert all the letters to uppercase and store the result, whatever that result would be. We could store that in memory. And then our final step may be to just display the user or display a message to the user on the screen showing the user their uppercase first name. All right, a pretty simple set of instructions. But our problem here is this is in English, right? If I just typed this into the computer, it wouldn't do anything. It doesn't know how to do this. So, like it says here, collectively the instructions of a computer program are called an algorithm, which we've discussed already. And I'll redefine that again, just so we're clear. An algorithm is just a set of well-defined steps for performing a task, and they need to be sequentially ordered. Otherwise, they're not a set of instructions, they're just a list of things, right? So we can understand those instructions pretty well, right? If we were to look at this, we can make sense of this, and it kind of logically makes sense to us as people. But if we just gave that to the computer, it would not be able to execute, right? We discussed the CPU before. The CPU can only process instructions that are written in machine language, and this is something that we don't really talk about, or we talk about it, but we're not really going to look at machine language. If we took a look at an actual snippet of machine language, all we would see is just binary numbers, zeros and ones. So unless we would want to type out 10 million zeros and ones to get someone's capital name, right? That would not be great. So instead we use a programming language, and these programming languages that we use allow us to use words, phrases, and symbols instead of binary numbers. So there is software in place that translates the programming language into machine language, right? And we'll discuss what that is here in a second. So basically, the CPU requires binary to execute the instructions. Well, we can't type binary, so we're going to use like a middleman here. So we're taking our English, we're turning that into a programming language form, and there is going to be some software we can use that takes that programming language code and turns that into binary for the CPU. And we don't ever have to look at that or see the binary, it just does it for us. So the programming language we'll be using is in this class is going to be Java. So what is Java? Very brief history of Java. Java is an object-oriented programming language, which we'll discuss what that means. But it was invented at Sun Microsystems, which is now Oracle. So Oracle now owns Java. Java can be used to develop several types of software. We can develop standalone applications that run on a single computer. So this is going to be the one that we use in this class, is this first one here. You can also use Java to write web applications and applets that run in web browsers. So Java can be used to write all kinds of different software. But like I said, the kind we're primarily concerned with is a standalone application that runs on a single computer. So let's talk about, what programs are and some different components of a program. So every programming language, Python, Java, C#, C++, any programming language, right? They all have some things in common, which is good because it allows you to take one programming language that you know, and maybe it's not so hard to pick up another one down the road because you know these things are going to be similar, right? So this table kind of talks about some common elements found in pretty much every programming language that there is. And these may be different depending on what programming language you're using, but they all have these things. So the first one is keywords. A keyword in a programming language is just a word that is reserved for something special. So if I were to use a keyword in my program in the wrong place, it wouldn't work because the keyword means something special. We also call these reserved words because we can't use them anywhere but where they're supposed to be, if that makes sense. An operator is just a symbol or a word that performs operations on one or more operands. And we think about operands as usually some kind of data item like a number. So our addition operator would be the plus sign, right? X plus Y plus would be our operator here. Punctuation. A lot of programming languages require us to use punctuation characters, which serve specific functions. So punctuation characters can mark the beginning or the end of a statement. They can separate items in a list, so on and so forth. That's our punctuation. Programmer-defined names are kind of the opposite of a keyword. All right, so a keyword says you cannot use this word anywhere besides its intended place. Programmer-defined names are words or names that we define as programmers, and we can use those wherever we want. We often use these to identify places in memory, right? Because we said that things that we use in our program, our data, is saved in our memory. We can identify those data points with a name that we create, and we call it a variable. So we think about, x equals 4. X would be our variable there, and whatever x is, we know its name. It's a programmer-defined name. We call these identifiers sometimes as well. And the last thing that most programming languages have is syntax. Syntax just refers to any rule that you need to follow when you write a program. So syntax is kind of the law of the language, which tells us, where do your keywords belong? How are your operators used? Do you have punctuation characters? Where do those punctuation characters go? That kind of thing. That's all syntax, the rules of the language. So Java, which we're using in this class, has a very different syntax than Python, for example. They're very different in terms of syntax, but they both have all of these things. They both have keywords, they both have operators, punctuation, programmer-defined names. They just have different syntaxes. So here's an example of some code, and I'm going to kind of walk through the different pieces of this code and kind of discuss what each of these things means. So this is a very simple program here, and we're going to talk about what each of those things means. So my keywords I have underlined here in red. These are words that Java knows means something very specific. So if I were to use the word public, for example, in the wrong place, Java would not let me do that because it knows where public belongs, and if you use it somewhere else, it's not going to like it. So all of my red underlined words here are my keywords or my reserved words. All of these are my programmer-defined names. Payroll and main are also programmer-defined names. These are things that I, as the programmer, when I wrote this little program, just made up, right? So these are names that I created. I have some operators here. I have the equals sign, which the equals sign in Java does not actually mean equals. We call that the assignment operator, and we'll talk about what that means when we talk about all of the operators later. But that's our assignment operator, and this is my multiplication operator. So this is what operators look like. And my punctuation characters, I have the semicolons here at the end of my statements, and I also have these braces here as well. And we'll talk about where all of those go in a little bit. So I just want to talk about some terminology here, because a lot of people get tripped up on terminology. I just wanted to address it. When we talk about a program, we talk about our program in terms of lines, and we talk about it in terms of statements. So a line is exactly what it sounds like. It's just a single line in the body of the program. So line 6 is right here. Double gross pay is assigned the value of 0. That's line 6. A statement is a complete instruction that causes the computer to perform some kind of action. This screenshot shows a statement that calculates the sum of 3 and 9. So in Java, our programming statements will always have a semicolon. So if you're wondering, is this a statement or is this a line? If it has a semicolon, that means it's a statement. I'm literally telling my computer to do something specific, right? That's a statement. Line 4, for example, is just a curly brace. It doesn't do anything, it's a curly brace. This right here, int hours is assigned 40, semicolon, is a statement, right? So, like I said, our statements always have semicolons in Java. Every statement that we write will have a semicolon. It's often the case that a statement will occupy a single line of code, but it could take up multiple lines. It's possible that that could happen. So if we look here at our example, all of our statements are in this little code screenshot are on one line. It may happen that they're on several lines. So let's talk about variables. A variable, and I've discussed this earlier in the video, but a variable is the most fundamental way that a Java program stores a data item in memory. So we refer to variables, they're very closely tied to memory, right? RAM, our random access memory. All a variable is just a named storage location in our computer's memory. The data stored in a variable may change while the program is running, hence the name variable. So for example, if I have in my code, and we'll discuss what data types are later, right? Let's say that I have this programming statement. Int x is assigned a value of 4. What I'm doing, and I'm going to pretend like this is my RAM up here. Let's see if I can write legibly. What I'm doing is I'm telling my computer, hey, find a free spot in memory, name it X, and slap the number 4 in there. Right, so now anytime I want to refer to this location in memory, I can call it by name, X, right? So maybe later I have a statement that says X is now assigned a value of 12. Whatever value was stored in X would be replaced with the new value, right? The value can change. The variable is the storage location in memory. Variables are symbolic names made up by the programmer that represent locations in the computer's RAM. So that's the key takeaway here. A variable is just a name that I create as the programmer to refer to a place in memory somewhere. And we'll talk about variables a lot more when we actually do our coding stuff. But I did want to introduce them. So we've talked about programs, we've talked about statements and variables. So what is source code? Source code is just the file that our programming statements are saved in. So a source code is my file, right, on my computer. Our Java source code files will always have .java of the file extension, right? So instead of program.txt, it would be program.java. And that's lowercase java. And we use a text editor of some kind to type our programming statements. In this class, we're using IntelliJ, which our last lab 3, was getting IntelliJ set up. And that's what we're going to use to actually create source code. All right, so if you remember earlier in the video, I said that there's like a translation process that happens, right? The CPU needs binary to execute instruction. We can't type binary, right? So we type out Java commands or Java statements. How does our Java statements get turned into binary? Well, there's a process, right? So there's something called the compiler, and you'll learn a lot more about the compiler in some of the later computer science courses. But a very basic overview of what the compiler does is whenever you save your source code to that file, that .java file, the Java compiler can be run. And if we're using IntelliJ, that kind of happens for us when we click the little play button to run our code. It's gonna run the compiler. But you can do this by hand. You can compile the code by hand. You got to type out some commands in your command line to do so. But either way, the compiler is being used. All a compiler is a program that translates source code into executable form. So this is kind of the first step of that translation into binary. Any syntax errors are uncovered during compilation. So a syntax error is probably the thing that you all are going to struggle with the most in the course, and that's just violating one of Java's rules, right? You forgot a semicolon here, you're missing a curly brace here. All kinds of syntax errors can happen, and syntax errors are caught during compile time. We call those compile time errors. All a syntax error is, like I said, you just violated the rules of the programming language. Your program will not compile into executable form until you fix those syntax errors. The compiler will not translate your code into executable form until you fix those errors. So it's really important when you're looking over your code to make sure that there are none of any errors in it, otherwise it cannot be executed. So once your program is free of syntax errors, the compiler then creates another file that holds that initial translation, right? And this translation is not in binary yet. That happens here with the Java virtual machine. So the compiler translates our Java source file, right? We just talked about that. It translates our code into something called bytecode. Bytecode is not machine language. It's not quite binary yet. It's pretty close, but it's not quite there. So the CPU can't take bytecode and execute it. There's one more step that has to happen, and that is called the Java virtual machine. What the Java virtual machine does is it kind of acts like a middleman between the CPU and bytecode, and it'll take our bytecode and execute them as it reads them. So we call the JVM, or the Java virtual machine, an interpreter, and we call Java an interpreted language because it uses an interpreter, right? It's not like critical that you memorize all this stuff. It's just important that you know it's out there. Java is a compiled language because it needs to be run through a compiler. And it's an interpreted language because the JVM the JVM interprets bytecode, right? That's the key takeaway there. So the TLDR of that, right? We start with a text editor, in our case, IntelliJ. We're going to type out some Java code and we're going to save it to a source file, right? That's our next step. Then we're going to try to compile our code and make sure that it's free of any syntax errors. If it is, then the compiler will save our translated instructions to a bytecode file. And then the JVM can actually run that bytecode file as executable code, right? So this last step here, the JVM running bytecode, is what actually brings your application onto the screen and lets you interact with it. I'm not going to spend too much time on this, but the JDK, or that thing we downloaded in Lab 3, right, just stands for the Java Development Kit. It used to be called the SDK, the Software Development Kit. There's 3 editions of the JDK that you can download. We're using Java SE. This lets us write Java programs. The other 2 are for huge enterprise business applications and micro applications for things like appliances like smart fridges and your light bulbs, your smart bulbs, all that stuff. That would use the micro edition. But we're using the standard edition of the JDK. Integrated development environments. There are all kinds of IDEs. What an integrated development environment does is it combines the text editor, it combines the compiler, the debugger, and a ton of other utilities into a single application, right? So this is actually incorrect. We're using IntelliJ in this course. We were going to use VS Code, but we changed it at the last second. But rather than using command prompt commands and memorizing all of those command prompt commands to compile your code, to debug your code, to run the bytecode file, we don't have to worry about any of that with an IDE or an integrated development environment. It's all combined together. So in IntelliJ, we just click the green play button and all of that happens for us. All we have to concern ourselves with IntelliJ is the quality of our code or our program. And okay, I was making sure I had the right slides. This video is getting a little longer than I wanted it to, so I'm actually going to cut some of the material out. Let's talk about what an object-oriented programming language is and some aspects of that, and then I'll move on to the next video. So object-oriented languages are centered, as it sounds, on creating objects, right? They're object-oriented. All an object is just a software entity that contains some kind of data and some kind of procedure, right? So it's 2 things that we're focused on in an object: data and procedures. Data contained in an object is what we call the object's attributes, right? So let's think about a student object. If I wanted to create an object that models a student, what kind of data would I want to know about a student? Maybe the student's first name, maybe their last name, maybe their GPA, what courses they're in. All of that stuff is data about a student object, also known as its attributes. The other thing that we like in objects is procedures, right, or behaviors. And these are things that the object performs, that the object can do, and we call that the object's methods, right? So attributes and methods are the important things in object-oriented programming. What actions might we want a student to perform? Well, maybe we want them to check their GPA. Maybe they can enroll in a class. Maybe they can drop a class. Maybe they can check their grades, right? All of those things are actions that a student object can perform, otherwise known as methods. So attributes is the object's data. Methods are the object's behaviors or actions. And we're going to talk about these a lot more as we move on in the semester. I did just want to introduce them here. We do have two more things we use in object-oriented programming. That is encapsulation and data hiding. Encapsulation lets us combine our attributes and our methods into a single object, right? So in the old way of programming, right, your data would have to be separate from your procedures. With object-oriented programming, we can actually combine our data and our procedures together into one object. Data hiding allows us to make specific things about our object private to the object itself. And I'm not going to spend too long on that. We'll talk about public and private later. If you do review these slides later, like it says here, this is just to kind of very briefly just tell you object-oriented programming is a thing. It exists. And here's some basics of it. We're going to learn a lot more about this stuff as we progress through the semester. So that'll do it for this video. In the next video, I'm going to talk about some things that are specific to Java itself.